Now that we have a grasp of how we do networking up to the rest of the network and within the Fabric Interconnect and such, we need to understand how exactly the Fabric Interconnect is going to do networking down to the servers. One of the greatest benefits of UCS is our integration of networking from end to end, from all the way up into our actual physical network and stretching down into our virtual layer. One of the ways we do that is with the Cisco Virtual Interface Card, otherwise known as the VIC. When Cisco first released UCS, the VIC was a big part of its initial success. And even today, the VIC is one of the primary options. I dare say if you're going to install UCS, you're probably going to install it with the VICs inside of the servers. So in this video, let's dive in and take a look at how exactly the VIC functions and why it's such a big deal. In order to grasp the significance of the VIC, we first need to understand the reality of configuring our virtual environments. And so this is an area where a lot of networking engineers, if we've been born and raised in the Cisco world, for example, we don't necessarily know all of the inner workings in this. But I tell you what, if we're going to be a data center engineer, then we absolutely have to understand how our virtual machines and virtual hosts all interwork and connect with one another. And so a big part of this is going to be the virtual switching world. Let's consider a virtual host. This is one physical host that I'm drawing out here. We've got several virtual machines on this host. Let's just draw out, let's just say 5 virtual machines. Now each of these virtual machines is configured with at least one virtual NIC. At least if we want them to connect to the outside world, that's going to be a requirement. And so we'll just draw that onto each one of these here. And this virtual NIC is going to connect into a virtual switch. Let's just say we have a V switch right here, and we're going to connect these virtual machines up to this virtual switch. And so far, all of this is inside of software. We don't actually have physical NICs or switches or anything like that inside of this host. Instead, this is all done in software. However, at some point, the virtual world needs to meet the physical world, and this happens here. We bring a connection in, maybe this is a 10 gig interface, maybe it's a 40 gig interface, and we connect it into the virtual switch. This physical connection is going to go up to some kind of physical switch, so maybe this is our Nexus 9K. And so from the outside world, we see that our physical switch is connected to our physical host, but then when we get into the virtual world, we see that this connectivity actually extends all the way down to the virtual machines. And this virtual switch down here, by the way, this is one of the challenges of the virtual environment, because we in the networking world, we don't always get to set the policies and the configuration of these vSwitches. A lot of times our server teams are responsible for this. And this gets to be harrowing in some cases because we in the networking team, we're working up here and we work hard on building this network policy. And then down in the virtual world, hey, these virtual machines can just talk to one another and those packets will never hit our physical switches. And therefore our policy is kind of useless in certain cases. Now, if you're working your way through the DCCOR course, then earlier on in the Domain 1 section of these skills, we talked about how ACI can extend that policy into the virtual layer, and we can do that a number of different ways. Now here's a question for us. Why do we have these virtual switches? And the answer is actually pretty simple. Now, the reason is that if we were to simply forward our virtual machine traffic up to the physical switch, and let's just say that the virtual machine that we're trying to talk to exists in the same host, well, we know that our switches are unable to bring a packet in and send it out the same interface. We can't simply forward traffic up to the Nexus 9K and expect it to forward it right back down. And so these virtual switches were created. This is why we have them. But again, they cause some problems for us that we need to resolve. Now these vSwitches are going to be able to switch traffic downstream like we just talked about here between 2 virtual machines. However, upstream switching is done via pinning. And that should sound a little bit familiar because we just spent quite a bit of time talking about pinning. This is how the Fabric Interconnects behave as well. We're going to take a virtual machine and pin it to a particular uplink, and then maybe we have a second connection coming down into this virtual switch, and the second virtual machine connects to that link. This allows us to have all active connections, so active upstream, even if we're not port channeled, and the way we do that is again with pinning. So all of the same logic that we use in the Fabric Interconnects also applies to virtual switching. And this is why these virtual switches aren't part of our spanning tree domain, for example. We should never be able to bring traffic in one interface and send it right back to the other interface. Which means that our virtual switches should not be capable of introducing loops into the physical domain. Now we are able to have many virtual switches on a single physical host. So if we draw this out here, maybe we've got 3 different virtual switches, and again, we've got physical connections coming down into these virtual switches. The physical cables, by the way, those are coming into physical NICs on this host. So we have 2 physical NICs here that are terminating these connections. We've got 2 physical NICs over here, and we have 2 physical NICs on the left. And so we see that as we build out these many different virtual switches, we have a lot of NICs showing up on this physical host. In this drawing alone, we've got 6 NICs. However, in real-world network designs, this can have up to maybe 10 or even 12 NICs on a physical host. And that's partially because we like 2 connections for redundancy to each vSwitch, but then we have to ask another question, which is, why do we have so many vSwitches? Why are we connecting these virtual machines up to different vSwitches? Why not connect them all to the same virtual switch? Well, the answer is because we like our different traffic types to get their own vSwitches. In other words, the vSwitch on the right here, this might be a management vSwitch. And we can, by the way, deploy what we call a VMK, a VM kernel port, onto this vSwitch. This effectively is just an IP address. We could almost think of it as an SVI. And we're familiar with the concept of virtual IP addresses being added onto a VLAN up here in the physical networking world. Well, we can do the same thing in the virtual networking world. And now this virtual host has an IP address on a particular subnet, and we can use that to create traffic flows, whatever that is. So maybe this is how we connect to this host to manage it. We come in via the physical network, down this physical link through this vSwitch, and connect to this VMK's IP address. Likewise, maybe we create a VMK over here, and this VMK here is responsible for live migration. Live migration is when we move a virtual machine from one physical host to another physical host, and we do it all while keeping that virtual machine online. It's one of the magical parts of a virtual environment, is to be able to have another physical host over here that's also connected up to the network, and we truly move this virtual machine from one physical host to another. And again, that virtual machine never goes down from a networking perspective. That's incredible technology, and we rely on live migration in order to accomplish that. But again, that's a different type of traffic that we'd want to have on a separate virtual switch. Now I know in this drawing I have VMKs alongside VMs. In a lot of cases, we're probably not going to put VMs on our management vSwitch, and we're probably not going to put VMs on our live migration vSwitch, but it's just how the drawing came together here. Now, just like management and live migration, we might have another vSwitch with VMKs attached for iSCSI connectivity. iSCSI is how we can connect to our storage area network. This is how we'd connect to our disks, our data stores that are located on the network somewhere, rather than having the storage locally attached. And that's all well and good. We haven't even talked about the primary way that we're going to communicate with our virtual machines. We could end up with a dedicated virtual machine just for the data connections for all of the virtual machines. And then we might even have another one for security. Let's say our security engineers want a dedicated DMZ vSwitch for virtual machines that are inside the DMZ. Yeah, we can isolate that with VLANs, but not every security engineer is comfortable with that. And so to have a separate physical set of connections that go down to a separate vSwitch, talking to VMs that maybe are a security risk, well, that's going to feel a whole lot better, even in scenarios where we're not necessarily dividing it up by physical host. So as we count this up, we've got live migration, we've got iSCSI, we've got management, we've got data, we've got DMZ, and we might even have other vSwitches added. So just in our example here, we've got 5 different vSwitches. And again, for the sake of redundancy and having 2 connections per vSwitch, well, that's 10 NICs. That falls right into this category of this range that we talked about. And so if you've ever walked down a data center aisle and you've seen a physical host with this many connections going to it, and you might have thought, well, wait a second, all of those are 10 gig connections. Are you telling me that we need 100 gig going to this physical host? Do we really need that much network throughput? And the answer is absolutely not. We might be using maybe, 8 gig on this. We're not using even close to the maximum amount of bandwidth on this, and yet we need all of these connections because we want to split up the different traffic types according to virtual switches. And each virtual switch, again, needing 2 connections for redundancy, it creates this awkward scenario where we're consuming a lot of network ports. And it's great that Nexus gives us a plentiful amount of 10 gig and even 40 gig ports these days, but at the same time, these ports are still expensive. It's one thing if we only have 2 or 3 virtual hosts, but as soon as we get into, let's say, 8 to 10 virtual hosts, well, now how many Nexus 9Ks do we need? And how many access layer switches? And do we need to go with chassis switches? We have to ask all of these questions just to get us the port count that is required in order to support this virtual environment. And sadly, at the end of the day, these Nexus 9Ks, they're kind of bored. They're barely processing the amount of bandwidth that they're capable of doing on all these 10 and 40 gig interfaces. Now, everything I've drawn out here is as if we're picturing this as a rack mount server. But what about a blade server? What if we're talking about a non-Cisco blade chassis? And so now we've got this situation where we've got these 2 network switches in here, and the 2 network switches are connecting up to the rest of the network as well. And maybe a blade is down here. Remember, everything comes back to physical connections. Maybe this blade only has a couple of connections up to each switch. And yeah, those connections can each be 10 or 40 gig inside of the blade chassis. But at the same time, how are we able to achieve the numbers? How are we able to get the amount of virtual switches that we want to support this topology? And so this becomes a big challenge as well. Now, certainly you can look at this and say, all right, maybe one solution is that we just abandon this idea of deploying virtual switches per type of traffic. Maybe we don't isolate our traffic among different vSwitches. And that's absolutely a way we could go. I mean, way back in the day, the hypervisor vendors, they all highly recommended this as the methodology. In fact, they said that this is really the only way they're going to support it. And that set of rules has really laxed over time. They will absolutely support a topology where we put all of our VMs onto the same vSwitches. But now we have to worry about quality of service. Now we have to worry about traffic contention. Live migration and iSCSI, they take up a lot of throughput, especially live migration. And then you have storage, by the way, which maybe isn't quite as much bandwidth. It certainly can be a lot, but at the same time, it's very latency sensitive. And so we want to make sure that our VMs, our data and our management traffic, which is less critical, and even live migration can be less critical because it could just be resource contention we're trying to resolve. We can't let that type of traffic overrun our storage. And so we get into this problem where the only solution is going to be to combine all of these onto maybe 2 different vSwitches, and certainly we can make that work. However, at the end of the day, that does create more problems, and so at some point we've got to come back to the idea that we have to try and get back to this topology if we can. So this is where the VIC is going to come into play. What we have here is we have a server, and we've got a lot of different vSwitches in here that we want to connect to. However, again, we want to bring in as few connections as possible while still maintaining our connectivity, our topology that we want to achieve. And so the way we're going to do this is we're going to deploy the VIC. The VIC, the virtual interface card, is a piece of hardware. It's going to look and act like a NIC, really technically a converged network adapter because it's capable of both Ethernet and fiber channel. And when we have that, we call that a converged network adapter as opposed to a NIC or an HBA. And so we're going to install this VIC into a host. It's actually a physical card. It looks like a NIC. But the VIC is able to create multiple virtual NICs, we call them VNICs, that show up in the host. In other words, I might have a pair of VNICs here that connect into this virtual switch on the left. And then I have a pair of VNICs right here that are going to connect into the virtual switch on the, well, to its right. And we can carve this VIC up into as many VNICs as we want, really up to 256 on most VIC models, which should be plenty. We never need that many, I would hope. But at the same time, it allows us to create as many connections into the virtual layer as we desire. And I know what you're thinking here, which is, all right, Jeff, so our VIC is effectively virtualizing 8 separate physical connections down. Maybe upstream we've got 2, I'll just draw them as really thick connections here. Maybe we've got 2 40 gig connectors upstream. So what's the point of virtualizing this? Well, the point is that this virtualization is done in hardware, on ASICs. In other words, it's basically carving out as close to physical NICs as possible. This still allows for traffic isolation to occur. We want this traffic to be isolated in the physical host world and even within the VIC. And then yes, at some point it is going to get aggregated onto a single connection. At some point, all networking traffic does, even if it goes up to a physical switch in a separate connection, that physical switch is going to aggregate them and send them up a dedicated uplink. So the fact that we're doing it on the network card instead of on the upstream switch shouldn't be a big problem. Furthermore, leave it to Cisco, but UCS supports very stringent quality of service policies. We're able to deploy whatever policies we want onto this connection so that we can isolate the iSCSI traffic and give it priority. We can give bandwidth reservations to the live migration traffic. We can deliver the policies that we want to enforce even though we're aggregating it onto a pair of connections. Meanwhile, by the way, as far as the physical host is concerned, it's really happy because it has all of the dedicated NICs that it wants. It has redundancy on those NICs. We have 2 per vSwitch, for example, and we can have as many vSwitches now as we want. This not only checks a whole lot of boxes on the virtual space, but it checks a whole lot of boxes in the networking space. We can apply our policies downstream, whether those are security policies or QoS policies, all while maintaining the ideal configuration of the virtual hosts. And as if that's not enough, because the VIC is a CNA, because it's capable of fiber channel connectivity, we can use the VIC to carve out virtual HBAs. I'll draw them over here, squeeze them on here. These right here would be considered VHBAs. Host bus adapters are how we connect to fiber channel, and so they're essentially going to connect down. We don't call them VMKs because it's not using IP and IP addresses, but it's going to connect in such a way that the host can access the fiber channel domain. And that doesn't change our upstream connectivity because we've got 2 40 gig connections, let's say, and these are now running fiber channel over Ethernet. So our fiber channel connectivity just rides across the Ethernet connections via FCOE. Now on top of everything else, we come back to that idea of the blade chassis that we talked about. And the blade chassis are going to have very few physical connections internally. And by the way, UCS is no exception. We only have so many of these connections that we can extend down to the blades. And so by connecting in the VIC, we solve the pain point of saying that, well, blades only have so many physical connections, and therefore this topology in here is just not possible in a blade chassis. Well, now it is. It absolutely is possible inside of the UCS environment, and it's all thanks to the VIC with how we can accomplish that. Now, one last note, by the way, is that we've been talking about this from a virtual host perspective. This works great still from a bare metal perspective. If we have a bare metal application that needs a lot of these physical connections to attach to it, and we're installing that into a blade environment like UCS, well, that could cause a problem. But instead, because of the VIC, it will work even in a blade environment, again, whether it's a virtual host or whether it's a bare metal application. So hopefully now we have a clearer picture of why the VIC is a big deal, even in modern networks today. The idea here is that our virtual hosts, they need multiple vSwitches for VM connectivity. And the reason we have multiple vSwitches is because we like to isolate different traffic types. We looked at a lot of those types, by the way, so iSCSI for storage and live migration. Those two especially can be in contention with one another, but we've also got management and DMZ and data traffic and such. And so the Cisco VIC is going to do its job by virtualizing this concept of physical NICs. So now the host thinks that there's a lot of physical NICs coming in, but those physical NICs are actually virtual NICs or vNICs. Those vNICs are created by the VIC, and it's created in hardware, so it might as well be physical NICs, especially with the way that we apply QoS policies and really make it so that we can do exactly what we want in the virtual space from a networking perspective without being limited by the physical connections we have. I hope this has been informative for you, and I'd like to thank you for viewing.